Okay, we should get started. It's already a couple minutes late, so sorry about that. Okay. Right, okay, so here we are. Where are we? We're week 8 now, right? We have the midterm this week on Friday. It'll be in class. It's a traditional midterm on paper. Okay, no notes or anything are allowed. No calculators, of course, but they wouldn't help you. And so the plan is that Wednesday we'll have a review session, and that'll be the whole lecture on Wednesday will be dedicated to reviewing for the midterm. Okay, so you can come with questions. Now, I don't have a practice exam, and I don't really have a study guide either. I'm not sure what I would put on the study guide. I mean, the quizzes are a good study guide. You should be able to look at, the answers, and there's some feedback stuff in there. Hopefully that shows up for you. I know I've messed that up in the past where I didn't check a certain box, and so the students couldn't actually see that there's like some feedback that shows up on the questions that you got wrong. So hopefully that shows up. And here's a good study guide too. Here's the topics and the lectures. So of course you should know about the natural numbers, okay? How they're defined inductively, and there's some basic operations on natural numbers that are like recursive functions, okay? How you do that in Pirate, okay? And then we had structured and conditional data, like the data types in Pirate, and sort of counting the number of elements of a data type, and interpreting them as sets, and like products and sums, product and sum types, okay? And collections and recursive data, so you should be pretty well versed in programming with lists, writing recursive functions on lists, okay? And that's kind of related to higher order functions where you got things like map and fold and that sort of stuff. And then there'll be a bit about trees perhaps, and state and equality, like references. We talked about that a little bit, but not too much. And there will be perhaps a little bit about abstract syntax and parsing that we've started on a little bit. So yeah, that'll be more of a focus on Wednesday. Okay. Let's see. Also, I guess someone told me that I didn't realize this, but I guess I miss questions a lot of the time, like raised hands. And I didn't know that, so don't hesitate to just speak up if I don't see you, and I'll try to be better about doing that. Okay, and and so I guess I could say one thing about, because we never really explained, that wasn't really my plan to explain, but like red-black trees, right? We never really talked about red-black trees at all, so I don't want to spend a lot of time on it, but I can just point out something that is not very obvious, because I think there's probably some confusion about what in the world is going on with red-black trees and why they even make sense. And one of the things is like, why do you need red nodes? Or so if you look at the definition, the properties, let me bring it up. Let's look at the properties. Here they are. So all nodes are either red or black. Okay, the root node should be black. All the leaves should be black. Red nodes cannot have red children, and the black height of any node is like balanced, or whatever, however you want to say this, that any path from any node to a black leaf has the same number of black nodes, okay, and then it's also a BST. And so you could look at this and say, actually, you could have a tree that is like all black nodes that satisfies all these things. There's no reds at all. But then if you think about what such a tree would look like, it would have to be a perfect tree, okay, in order to satisfy number 4. So I don't know if I could draw an example, or I wonder if I have this thing that might be useful. Oops, wrong one. I wonder if we could use this. Let's try it. So let's say you've got like a black root, and okay, maybe it's something like this. It's an interesting little tool for visualizing S expressions as trees. Okay, so here's an example red-black tree where the root's black, these nodes are black, and all the leaves are black, and it actually satisfies all the properties. Okay, but it's a perfect tree, so it's perfectly balanced. So it's, any perfect tree with all black nodes is a red-black tree. Okay, but that's totally fine, because the whole point of being a red-black tree is that you should be balanced, so that lookup is efficient, so that the length of any path is like logarithmic in the number of nodes of the tree. Okay, so if you go and try to add some children here, you'll find that it's no longer a red-black tree because it violates property 4. So now, say you start the root, well, there's a path of 3 black nodes to a leaf, and there's a path of 2. So it's not the same. And so this is where the red nodes can come in. The red, you could do this instead. Something like this, I think. Would this work? It might not be exactly a red-black tree, or is it? Okay. All right, so what red nodes do is they give you a little bit of leeway, kind of introducing some unbalancedness. Okay, but it's a restricted sort of leeway because, well, red nodes can only have black children. So the worst that you could do is just kind of alternate red and black. And so then the longest path that you can come up with is black, red, black, and then the shortest would be all black. And that's why you have this property that the longest path is no more than 2 times the length of the shortest path. Okay, because the longest one has to alternate between red and black, and the shortest would be all black. And so that's why it's sort of approximately balanced, and you get good lookup, and it's like log time for all the operations. Okay, so once you see it like that, it's fairly straightforward, I think, what the idea is. Okay. Now, let's look at the chapter for this week. Just take a look. So the reading is chapter 24, and it's about parsing. Okay, and there's a bit of stuff here that we kind of already looked at. Okay, some of this terminology of what's a type checker, that it will take a program and kind of tell you true or false depending on whether it's well typed or not. Okay, there's an interpreter. I skipped that. Okay, the interpreter will take your program and run it somehow to produce the answers. Okay, and then there's some other things like a pretty printer can kind of print them out in some pretty format. Okay, and some other ideas, and these names are not really set in stone as the only name. Okay, if you go around the literature, you'll find different names perhaps for some of these things. Okay, and then there's also the compiler that takes programs in one language and produces related programs in another. Okay. Let's see. Right, but here we're going to focus on parsing, which, so if you look at all these things, they kind of have one thing in common. Observe that in each of these cases, we have to begin by consuming the program. So there's the first step, even for all these things, is you have to parse in the program into a representation that can be worked with. Okay, and so that's why parsing is really important. Okay, it's a very general activity whose difficulty depends on, the complexity or degree of ambiguity in the input language. Okay, we're going to be kind of lazy about this, and we're going to choose a source language that has no ambiguity at all, and that is easy to parse. All right. We're just going to kind of sidestep the whole issue of ambiguity by using S expressions. So we've looked at this stuff already a little bit. Okay, and Pirate has some libraries for S expressions, and we looked at those too, right? So you can import SX, and then here's this function you can use from that library, s.read_sx. You give it a string, and it'll give you a value of the SX data type, right? Or it'll throw an error if this is not a well-formed S expression. So, and the way that we're going to structure our parser is kind of like what they're doing here, where you first use that read_sx function to parse the string into an S expression, and then there's kind of a phase 2 of translating the S expression into your abstract syntax. So here they introduce some abstract syntax that should look fairly familiar to us. It has a different name. They're calling it arith_c, and it has 3 constructors, one for numbers, and then one for plus and multiplication each. Okay, and then they give a function called parse. It takes an S expression for its input and produces arith_c. So this is kind of just a conversion or a translation from S expressions to the abstract syntax. And it's kind of a big clunky thing in a way. And so kind of what I want to do is like kind of take this parser that they give and modify it to try to reach the strategy that we're going to use for our parser. It's not going to be quite like this. Okay, but let's take a look at what it's doing. This is kind of the most straightforward way to go about it. So we say, okay, what kind of S expression is it? Let's do cases on the argument S. And then, so if you recall the constructors of S expression, let's try to find them. Where is it? Okay, there were 4 constructors. There's list, but then there's also num, string, and symbol, sim. But here we're only handling 2 of the cases because our abstract syntax only supports numbers and then plus and multiplication, which will be lists. So for string and symbol, we'll just raise an error. Okay, so we have 2 cases to consider. In the num case, it's trivial. We'll just produce the abstract syntax for a number. Okay, but then in the list case, that's when it's going to be either plus or times, or an error. Right? And so what will we do in the list case? Well, they're reusing the name S, and so they're using the shadow keyword so that Pirate will let them do that. Okay? I don't know why they would do that, but so now inside of here, S refers to that list. So now we're going to do cases on the list. If it's empty, that's an error because, well, we expect there to be either a plus or a times there. Really, we expect the list to have 3 elements, not 0. So that's obviously an error in that case. But then when it's a link with what we assume will be an operator in the first position, it's just an SX, just an S expression there, and then the rest. And what will we do? Well, let's go ahead and pull out the next 2 elements from args. Either of these operations could fail, right? If args is empty or only contains 1 element, then we'll also have an error thrown from one of these functions. But if we keep going, then we'll say, okay, again, this could throw an error too. This probably won't even type check if you use a type checker. But here we're saying opt, which is an S expression, it should have an S field. So let's say, well, if it has an S field and it's equal to plus. So there's a bunch of stuff in here that will kind of like implicitly fail if something goes wrong. So that's one of the reasons I don't like it. Let me look at this again. See, there are only 2 of these constructors have an S field, and these ones don't. So if you say opt.s, where opt was a list or a num, then that'll be an error. But anyway, if it was a plus, then okay, we'll produce our we'll say plus C and recursively parse the left and the right arguments that were those S expressions in the list. Else if it was a little times thing, then we'll say multc instead. All right. So this is, I suppose you could call this a recursive descent parser. So the grammar, they don't even give the grammar, unfortunately. So we could write down the grammar here that they're using implicitly for the language. Okay, so let me write down the grammar. Whoops. I'll say an expression is either a number or, plus e, or times e. Okay, where n is a number. And so, well, I don't know actually if this qualifies as recursive descent or not. So the idea, though, is that at any point when you're parsing, you only have to look at one symbol ahead in the string. Right? So the idea is that if you're parsing, you can look at the next symbol and say, well, if it's a number, then okay, we'll parse it as a number. Or if it's a plus symbol, then we'll parse it as a plus. Or if it's times, then we'll parse it as a times. Of course, these parentheses kind of complicate the story, I guess. But because technically, actually, if you look at the next symbol, there are two different types of expressions that start with a parenthesis. So maybe it's technically not right to say that it only requires one look ahead. But it's very straightforward to implement a parser for a grammar like this, where you all you have to do is just look at the next symbol, and that'll tell you how to proceed. Okay, so at 4100 you'll get more into that kind of thing in a more rigorous way. Okay, but so this is the parser that they give, and then they have some tests to check it out. All right, so what I want to do is copy this code. Let's go ahead and just copy it all for now into a file called parse.r in the in-class repository. Copy everything over. And well, first thing we have to do is get it to type check. Okay. So it's not type checking right now. Oh yeah, and so the first thing that goes wrong, let's see, it says line 19. It's this op.s thing. Okay, because as we've seen, not all the constructors of the SX type have the S field. So this will be a type error. So we're going to have to do something a little different there. And what I'll say, since op was an SX, op, we want it to be the symbol constructor. So in that case, we can refer to it. Otherwise, throw an error. So that'll fix that one. And now it type checks and compiles and runs. So that's good. Now I want to do a little more cleanup. So first of all, I'm just gonna introduce a type synonym to make it a little easier to refer to this SX type. Okay, so you don't have to do this, of course, but it'll make it a little nicer. Okay, and then I suppose we don't actually need this L module to be imported because we can replace these with args.get, okay, as a method on lists. So this is just a little cleanup right now. Okay. But now what we really want to do, the main thing that we want to change here is that we don't want to raise errors like this when there's an error. That we want to use the result type instead, right? So that's what we'll do first. So I'll have to bring in some result type code. I think where I can find some. Don't want to use a solution file. PA, that was in PA3 we had some, right? Yeah. So I'll go ahead and copy some of this stuff in. At the top. Should still type check. Okay. And now we want to change the type of the function to return result of arithc. Okay? Instead. And the test cases will now have to be changed so that the answers should be wrapped in the OK constructor of the result type. Okay. So now, of course, we haven't actually fixed up parse yet, so it's not gonna work. And it complains at line 61. Well, it's just complaining about the result type. But of course, we need to return a result now. Like instead of just num_c constructor, it needs to be OK of num_c. That's the first thing. And anywhere we were raising an error, we now will replace with the error constructor. So we're actually producing a value. We're not raising an error. We're just producing the value that signals an error. Okay, so we'll do that here too, and here, and that'll get us pretty close, I think. All right, where are we at now? Line 73. Okay, and now we've just got this issue to deal with, I believe, where, see, now that because we've changed the type of parse, it no longer returns an arithc, it returns a result of arithc. So we've got this parse thing is a result of arithc, and so is this one. But of course, the +c constructor expects arithc, not result of arithc. So you could do, so the most straightforward way of doing this is to use the seek function. Okay, we're going to rely on seek a lot, but seek is our primary tool for handling this kind of thing with the result type, where you've got, this is a computation that returns a result, and we want to be able to use the result. So what we can do here is to use seek. Say, well, seek parse argel, and then give it a lambda for taking the result, which I can call A1, I guess. Okay. And then we will continue. Well, we have to parse argr as well, so I'll seek that, argr, and give it a lambda for taking the result of parsing argr. And now, once we're in here, if we get to this point, now we can say +c A1, A2. And, well, we do need the OK constructor. All right? And so that's how we can fix this. All right? So we're not quite done because, let's see, line 80, that's here. We have to do it again for mult_c. Okay, so I'll just copy it. Mult_c. And there we go. Okay? So now we have successfully rewritten their parser that they gave us to use the result type. And so now one of the things that's nice about this is that it never throws an error. Hopefully not. We are using this equals function, so right, I told you not to use that. So maybe I should listen to my own advice and use eq instead, so you can be more confident that your code won't throw a runtime error, because this function is type safe. Okay. So now, yeah, if there's a problem parsing, the function doesn't just freak out and raise an error. It returns an error value in a controlled fashion. Okay. So the program never crashes or anything. It always produces a value. So that's good. Okay. Right. So we still have a good bit of time. So this is kind of like the most straightforward, naive way to do this, I would say, that I could think of. I mean, we've upgraded it to use the result type, but it's still kind of following the same strategy that they gave in the book. All right, and it's not too bad when your language is like this, when it's very small and simple. But this can get pretty big and ugly and complicated for a larger language. And so what I'd like to do is to lead us into a more principled way of writing a parser like this, so we can rewrite it a bit more and kind of re-strategize a little bit. Okay, and we probably won't finish this today, but we can get started. All right, and let's see. Not sure how to lead into this, but the main idea is to think about using functions that are sort of like coercion functions or conversions, where you assume that the input will be of a certain form, but if it's not, you return an error. Okay, so this is one way of using the result type. So let me show you what I mean. So what I want to do now actually is, instead of having one big monolithic function, I want to have a separate parsing function for each of the constructors. Okay, and so I'll say one for like num, parse num, and it'll take an sx and give you. We can make it arith, where the idea here for parse num is that it's gonna try. You could call it try parse num. That might be a better terminology. Okay, it's going to try to parse it as a number, and if it succeeds, then it'll give you an arith that's constructed using numc. But if it can't parse the sx as a number, it'll give you an error instead. Okay, so we'll have one like that, and then we'll have one for plus that does the same thing, but tries to parse it as a plus expression. Okay, and then we'll have one for mult as well. Okay, so we'll have these three separate functions that are sort of like try to parse it as a num, try to parse it as a plus expression, try to parse it as a mult. Okay, and then we can get rid of all this, and the main parsing function can just be like, try to do it as a number first, and if that succeeds, then okay. Else, try to parse it as a plus, and if that succeeds, then okay. Else, try to parse it as a mult. And if they all fail, then we have an overall parse error. Okay, so the logic of this parse function is very simple. It's just kind of a choice between, just try each one of these until one of them succeeds, and then that will be the result. And so we had a thing for that I introduced that I called parallel composition. And I called it plus, which maybe I could use a better name for that. I don't know, because I think that might be kind of confusing, calling this plus, because there are other kinds of pluses around. Okay, but if you look at this code, what it does is it takes an x and a y, each of type result of a, and it just looks at it looks at x and says, if x is an error, then go to y, so sort of default to y, or if x is not an error, then we'll use x instead. So we can use this plus thing to do what we want. Okay, so I could say plus parse num s, like try to parse it as a number, and if that doesn't work, then we'll do something else, and we'll do another plus, try to parse it as a plus. So maybe that's where it gets a little confusing. Sorry about that. Okay, and if that doesn't work, then we'll try to parse it as mult. And that's it. Okay, so it's kind of a nice little way of factoring the parser into some pieces. that also makes it pretty obvious what we're doing. Okay, it makes the parsing logic apparent in the structure of the code. Okay. Uh-oh. Huh? Yeah, it's over, but I think it's working, but we're just, it's trying to evaluate the tests, and it's hitting these things that are not implemented. So I think we're okay so far. Right, so, there's this word that gets thrown around sometimes about programming languages. It's declarative. Okay, it's sort of a weasel word, like declarative. So you could say this code is declarative now because it's sort of it just kind of like describes what you want without having a bunch of unnecessary operational details of how to accomplish that. Okay, but no, it's one of those words that nobody can really agree on exactly what it means, but this is sort of a more declarative style of writing a parser. Okay, but we have to actually implement these now. All right, so let's try writing parse num. Okay, it'll be pretty straightforward, I guess. Really, when is an S expression going to parse as a number? Well, it's when it's an S num constructor, and we just pull out the number, right? So let's do that. So we'll do cases on S. And when it was S num of a number, then we're OK with a num C with that number. Else, it's not going to work. And I'll just be a little lazy with the error message. OK. And so far, so good. We're still hitting these template expressions it's complaining about. But that's very straightforward. OK. Just try to parse it as a number. So now we can move on to the other ones. They're a little bit more involved. All right. So let's do parse plus. Of course, these two will be pretty much the same thing, right? So once we do one, the other one comes for free, pretty much. So how are we going to do this? Well, so the plus has that expression has 3 parts, and so we expect it to be a list. Okay, so we'll do a similar thing here, where we do cases on S, and we want it to be a list. Oops. And if it's anything else, that'll be an error. Okay. So far, so good. It seems to be type checking. All right. So now, once we've got a list, this is now L is a list of SX. And what do we want? Well, it should have 3 elements. Okay, it should be a list of length 3, where the first one is a plus symbol, and then the next 2 should parse as, arithmetic expressions somehow. Okay, so what can we do? Well, I'll say, well, if L.length is equal to 3, then we can continue. Else, it'll be an error, right? Okay, so in order for us to succeed as parsing it as a plus expression, it needs to be a list of length 3. So we can continue here. And now we'll say, okay, the first one should be a symbol with a plus. It should be a plus symbol. So it has to be a symbol, first of all. So let's see, L dot get at position 0. We expect it to be a symbol, right? And if it equals, I shouldn't use that equals, sorry. If it's a plus, then we can continue. Now, you can see this is still not super pretty, and there's much more that you can do to clean this up even further. But for now, it's okay. But there's still a lot of error cases. Okay, there are lots of ways for this to go wrong, of course, right? Right, like if the first element of the list wasn't a symbol at all, then that's an error. Or if it's a symbol but it's not equal to plus, then that's also an error. Okay, so all of these things need to be true in order for us to continue parsing as a plus. And now that we're in this situation, all that we need to do is recursively parse the second and third elements of that list. And then stick them in a plus C constructor, right? So that's where we'll have to use seek, because we're going to use parse recursively, or it's like mutual recursion. So we'll be parsing the element of the list at position 1. That's the second element. Okay? And doing this again. Let's see. There we go. Seek parse L dot get 2. And now the same thing from before. Think something's wrong?
No, never mind. I thought I think that you mentioned that.
I think it looks okay. Yeah, I mean, we didn't get a parse error. So there we go. That's plus. Now I think we're still getting errors because we haven't finished this one. But so this is still, I mean, it's kind of big and clunky still. So it's not really ideal. So there's more that we can do to clean this up. All right. But first, let's just try. Let's see if it's right by filling in the same thing for parse mult. It's, you know, it's all the same except we expect it times instead of plus, and we'll produce a mult C constructor. And let's see what happens now. All right, passes the test. Now maybe we can look at the code a little more closely. I mean, yeah, basically you see there are plenty of ways for it to go wrong, but if all these conditions are met, then we finally produce a result in the end. Okay, and so the way that this parser works, again, is that it'll just try to parse it as a number. And if parse num of S returns OK of an error C, then that'll be the result. Okay, but if it returns error, then we say, okay, forget that, try the next thing. And well, it's a plus, so it does the same thing. Okay, call parse plus S, and if that returns an OK value, then that'll be our value. Okay, so there is like an order. There's a precedence of how things should be parsed here, but it doesn't really matter because they're all, well, there's no ambiguity. If our grammar was ambiguous, then the order of these things would matter, right? But maybe you'd want to have mult come before plus so that, like, I don't know, so that it takes precedence over plus. But we don't have to worry about that. Okay. And so now one thing we can do is we can continue our little journey here of trying to improve the situation because it's still not really ideal. Okay, and we can take this idea that I've suggested already of kind of these conversion functions that might fail, like a try. Like take a S expression and just try to turn it into something like, and if it succeeds, then return OK with that value, otherwise not. Okay, so we can take that idea and run with it even more to clean this up. Okay, basically all these things where they could go wrong, we could actually factor these into more of these like try convert functions. All right, so for example, the very first thing that we do is that we say, well, it should be a list, right? The S expression should be a list, and if it's not, it'll be an error. So we could write a function that does that, and I could say like as list or something, right? It takes an SX and gives you a result of list of SX. But the idea is to take the SX and try to convert it to a list, like coerce it to a list, which is to say, well, if it's a list, then give me the list. Otherwise, it'll be an error. Okay, so else error as list, right? So it's rather straightforward what it's doing. It's just if it's a list, then pull out the list. Okay, and this should type check. Okay. And so then we could use this function now. Instead of doing the cases explicitly here, we could just use as list and sequence. We can sequence operations like this. So now I can say, well, how do we want to do this? Yeah, I'll say as list s, and then give it a lambda that takes the L, and continue. Okay, and I'll have to fix something here. Probably that. Okay, it doesn't buy us a whole lot yet. Okay, but the point is that you can take this idea and use it to kind of transform the whole thing, and it'll clean it all up. So what else could we do? Well, the next thing that we're doing is checking that it has length 3. Okay, and so my idea for doing this, I don't know. There's more than one way you could, but one way that turns out in the end to be nice, I think, is to combine it with as list. So I would say, well, we can have an as list 3 function actually, where not only are we asserting that it should be a list, but actually that it should be a list of length 3. So then it doesn't return a list, it just gives you the 3 values. Give you a product like that, okay? So then I could say, well, as list, what do we do? Seek as list s if l.length equals 3, then l.get 0, l.get 2, okay, so this is just kind of combining as list, but also asserting that it should be 3 elements, and then it'll give you those 3 elements. Something is wrong. Line 85. Oh. Okay. Right, and so now, well, once we have that, instead of using as list, we can use as list 3 instead. And the lambda will take not a list, but actually 3 S expressions wrapped up in a tuple, like that. And now we don't have to check if the length is 3 anymore. Now, well, let's see what happens. It might, what is it? See, line 91. Oh, right. Right now, where we were referring to the elements of the list by, L.get1 and so on. Well, now we don't have L, we just have them by name. So, like L.get0 is now S1. L.get1 is S2. L.get3 is S3. Okay. Compilation errors. Unable to infer the type. All right. So we're in this kind of like an awkward intermediate stage where I have to do something just to get it to work. But again, there are more improvements. Okay. Okay, this works though. All right. But so you can just run with this idea further. Okay. So what's the next thing that we do? Well, we check that S1 is a symbol that has a plus. Okay. So I could write a similar thing as sim perhaps, where you give it like the expected. It's a string. And of course, we don't actually care about the result this time. So I'll make it take the empty. It'll return an empty tuple. So the point is that if this returns like OK at all, then you're good. You don't actually care about the result. There's no output. Okay, and what will this do? Well, kind of the same thing. Just if it's a symbol, then that equals the expected thing, then you're OK. Else, error. And else. And OK. Something is wrong. I see. Okay, so now once you've got that, we can say as sim s1 plus, don't care, now where are we at now? Can we get rid of all these? Yeah. Okay. And now we've managed to clean it up quite a bit, and we're going to have to stop here for today. But so what we've done is we've kind of factor out some of these basic operations that we're doing into like generic procedures for like, try it as a symbol, try it as a list, and so on. And then the function that actually encodes the logic for parsing something as a plus expression becomes more declarative in a way, where you're really just saying, here's how to parse it as a plus expression. Try, it should be a list of length 3, and then the first one should be a symbol that's a plus, and then the next two, just parse them as expressions, and then you're good to go. Okay? And so what we'll do next time, like next week, I guess, is continue looking at this kind of stuff some more, because this is how we're going to be implementing the parser for our language. Okay? So don't go anywhere yet. There could be a quiz. Oops. All right. Okay. I don't know if there's anything from this lecture I can draw from for the quiz. So let's see. Give it a shot. Okay. All right. See you Wednesday.